What do this, or this, or this have in common with this? It's him, the guy who invented calculus. Hi, I'm Dave Dooling, Education Director at the New Mexico Museum of Space History. Today, we'll see how we use Isaac Newton's 3 laws of motion in hand controllers and rockets. You don't need anything but a cell phone and the right app. And here's a word of caution: don't copy what I'm doing. You could break your phone or model car, and I won't buy you a replacement. Here's a quick look at the laws that Newton wrote more than 300 years ago. 1. A body at rest will stay at rest unless acted upon by an outside force. Or, if it is in motion, it will stay in motion until acted upon by an outside force. 2. F equal ma, or force equals mass times acceleration. 3. For every action, there is an opposite and equal reaction. You experience these every time you ride in a car or when you ride a rocket. 1. When the car starts up, you feel like you are being pressed back into the seat. What's really happening is that your body wants to stay at rest as the car pushes forward into you. When the driver slams on the brakes or crashes, you feel like you are being thrown forward. Your body wants to stay in motion, but is restrained by the seatbelt. 2. You can tell if the driver pulls away from the light too fast or hits the brakes too hard by the force you feel through the seat or the seatbelt. If you know your weight and how fast the car took off, you can calculate the force. 3. When you push on something, it pushes back. Okay, how do these connect to the stuff I showed at the beginning? Rockets have guidance systems, otherwise they can't go anywhere except maybe into the ground. At their hearts are Newton's 3 laws of motion. Engineers have evolved inertial guidance, meaning using inertia and other laws of motion, since the late 1800s. Robert Goddard was the first to use a guidance system in a rocket in the 1930s in his work in Roswell, New Mexico. Here's a simple model. Inside a small box, I have a pencil running through 3 ring magnets. 2 are attracted to binder clips taped to opposite sides of the box, and the third slides free in the middle. Make sure that you have the poles facing north to north or south to south so they don't snap together. If I have a box on its side, opposing fields keep the middle magnet in the center. Turn the box and gravity pulls the magnet down until the strength of the fields matches the weight of the magnet. If I take it for a ride, I can measure how fast I speed up or slow down, or measure how rough the road is. This is an accelerometer. Game controllers have similar arrangements with MEMS, or micro-electromechanical systems. MEMS are also used as triggers so airbags deploy when a car collides, but not when it stops too fast. Your cell phone has similar accelerometers, so let's use it next. I'm using an app called Sensor Kinetics. The basic version is free, and you have to pay a little for the version that saves your records. Others are available, so check around and find the right one for your phone. Let's start by running with the cell phone lying on a table. 3 lines trace measurements in 3 directions, basically up, down, left, right, fore, aft. Notice that 2 reads 0, but the third reads almost -10. But the phone isn't moving. According to Einstein, the phone thinks it is accelerating upward at 9.8 meters or 32 feet per second. You would feel the same thing if you were in space and the rocket fired to send you to Mars. Tap the table and watch the lines squiggle a little. The app is measuring the vibrations coming through the table. NASA does the same thing on space station to measure vibrations on microgravity experiments. Next, I drop the cell phone onto a bed. While the phone is falling, all 3 axes read 0. That's free fall, often called 0G, but it happens because gravity is at work. Take a close look at the graph. It goes flat, spikes, and then flat again. What's going on? It's simple. First, all 3 axes go to 0 during free fall. Well, almost 0. If you don't release the phone just right, a tiny bit of tip-off can make the phone rotate, but it's close enough for us. Next, I got a big acceleration spike in one direction, then the other, when the phone hit bottom. The mattress was pushed inward and rebounded, causing a spike in the opposite direction as the phone bounced up and then a flat line as it coasted. The graph tells me how long the phone fell. And the value of 1g is 9.8 meters per second squared. From this, I can calculate that the phone fell 1 meter or 40 inches. Now I've taped the cell to the top of an RC car. I'm going to crash into the wall, something your parents won't want to try with a real car, and you probably should not do with your model car. I'll capture how fast the car accelerates, how fast it brakes, and how hard it stops when it hits the wall. On my first collision, I recorded a deceleration spike of almost 58 meters per second, or 5.7 times the force of gravity. Want to try more? Have your parents drive the car while you run your app in the back seat. Compare emergency stops with regular stops. Better yet, take the phone to an amusement park and measure the forces you experience on the rides. Make sure the phone is secure in a pocket so it does not fly away. Thanks for watching. Stay tuned for more Virtual Rocketeer Academy activities. In a later episode, we'll show how fidget spinners help point spaceships the right way.